Hello, folks. Thank you for coming to my talk. My name is Ignat. I'm from Cloudflare, and today we're going to talk about Linux kernel keystore. How many of you actually knew that Linux has a keystore? Oh, one person, two. Good. Thank you. A little bit about myself. I do, as announced, Linux at Cloudflare. I love Linux, and yeah, that's why I present from a Mac. I do system security and performance, and I enjoy low-level programming like Linux kernel drivers, bootloaders, and other stuff written in scary languages. Who here writes C or C++? No one. One person. Like you, like me, we're fugitive programmers since recently because NSA in the United States banned C and C++ to be used in big corporations. So. Yeah, so we're living on the edge. But again, and this is like, that will be actually a topic of my presentation today, like why memory unsafe languages are bad, and we will be talking specifically about cryptographic keys in the application memory. So let's kind of revise about operating system fundamentals and address space isolations. Like it says here, Linux address space isolation, but most operating systems provide that feature. So the idea behind address spaces is that you have a multitasking operating system. Obviously, you run several programs, and like, what does and each process has some kind of like memory region which it uses, and like, what's there in each program. So you have your application code loaded into the process memory, right? You have some kind of like libraries that your code may use. They're also loaded into the application process address space. You have some internal data. It can be like static data, global variables, whatever. And yeah, and also stack or stacks if you have a multi-threaded application. And you also run it on the operating system, so you have the so-called kernel space. This is kind of user space in literature. This is the kernel space. In kernel space, you have the code for the kernel itself. You have also static and dynamic data, global variables and stuff. And you have the drivers. So in the kernel, actually, the drivers share the same address space. So that's why it's very dangerous to load drivers into the kernel, which are you don't know where they came from. And also you have kernel stacks. And the idea behind address space isolation, so within each process, you can kind of access from every box to any box, right? So your main logic can access any data, any stack, any library. And same happens within the kernel. The kernel is just a big flat address space, and everything can access anything. But between the processes, you cannot access directly the memory of another process. So process 1 cannot access the process 2. And same happens within the kernel. So you cannot, from your process, directly poke into the kernel memory and see what happens. Now, let's actually zoom in a little bit and see what happens inside the process. So what kind of data do we store there? And roughly, you can categorize it to like some kind of internal state, your global variables, or some other like control stuff. If your application processes some input, it can be user or customer data, depending on what your application does. And the most importantly, if your application does some sort of cryptography like TLS or SSL, TLS, or the old name is SSL, it will have like cryptographic keys. And the problem is, like, if suddenly your application becomes compromised, so somebody hacks your application, because of the way how address space isolation works, like everything in the data section becomes compromised and accessible to the compromised code, right? But again, what's the outcome of that? Like, how bad is it? Well, technically, if your application internal state is compromised, well, it depends, right? It can be good or not so good. Like if an attacker can control some internal structures, it can trick your application to go into a different execution path, but depending on what the application does, it might not be as bad. Well, if your user or customer data becomes compromised, this is like much, much worse, right? Who here heard about Equifax a couple of years ago? Couple of hands. Yeah, so they had a breach. because they didn't update their Apache web server, and like, a lot of user data was exfiltrated, and it's a big problem. They had a lot of court decisions. They had to pay a lot of fines, but still, it's not the end of the world. They paid a lot of money, but they kind of still operate, right? But actually, if your cryptographic key becomes compromised, I think that's game over, right? So who here remembers a heartbleed? Who here did something about heartbleed? So like the whole internet got revoked at that point, right? So because if your cryptographic key is compromised, especially the one which represents, I'm back. Yeah, so basically your whole identity is compromised, right? So how does application keys can be compromised? So let's say you have your program executing, you have some stuff in the program's memory, right? But it might be that near to that in the same RAM, you might have a cryptographic key there, right? And this is how, yeah, and normally your application is designed to access stuff only, but if you didn't put safeguards in your memory and safe language, an attacker can direct your code to actually access this memory because it can. It's like not isolated in any way, and this is what actually happened within Heartbleed. So like out-of-bounds memory access is a very common pattern to exfiltrate your cryptographic key. Another way, like you can do like application, like arbitrary remote code execution, like there is nothing to discuss there. It's a game over. If an attacker can remotely control the execution of the code, it can direct that code to read any or write any memory within your process address space. So, and one example of that is Log4Shell. Who did it? Who remembers Log4Shell? Buffer reuse is a common concept. So this is like a complete program. If you get these slides, you can copy-paste everything, compile, and basically the problem is here. So here we have two functions. One is encrypt, which has a cryptographic key on the stack, and after another one which is a log function, but like we had a bug there. We forgot to initialize the message array, and basically if you compile this program without any extra features, security features in your compiler, you will see that the log function will actually leak the cryptographic key because you're not clearing the memory. So what happens here is in your stack is that you have the main code, which calls the decrypt data function or encrypt function. That function gets a key from somewhere, puts it on the stack, but when that function returns, it doesn't clean up after itself, so the data is still there, and the next function is actually can inadvertently access that cryptographic key. So that's why if you ever dealt with cryptographic keys and some kind of a compliance, you would always hear the requirement explicitly zero out the memory where the key was present, which is quite easy to do in C++, but very hard to do like in languages like Java and Go, where you have an explicit garbage collector. Another source of cryptographic key leaks is like plain bugs. So logging, as we just saw, if your application crashes, core dumps, GDB, ptrace, all these technologies, debugging technologies can actually accidentally leak your cryptographic data. Well, we can say like it's not a problem of application, they just fix all the bugs, but we know these bugs will always exist, right? So apparently we cannot really like solve this problem for everything, but can we do something specifically for cryptographic keys because they're a very high value target? And the common approach here is to actually create a different process which will have a different data section and put your cryptographic key in this another process. Then you write some small crypto logic and connect the two programs through a well-defined interface. So we call it like a key agent model. So you have two programs, one, your main program, which is network facing, it may contain bugs, and another, a small, very streamed down program which handles your cryptographic keys. And then basically the whole idea is to utilize the operating system address space isolation. So even if your main logic is compromised, it cannot directly access the memory of another project. So anyone uses SSH agent here? So yeah, it's one of the common examples of this agent model. But there are drawbacks to that model, right? Like if you want to protect cryptographic keys this way, you have to actually write 2 programs now, design this well-defined interface, and kind of like it has to be very strict down and control, so you don't have actually bugs in this agent program, right? And then you need to authenticate between 2 programs. Like we don't want our agent to accept requests from any process on the system, just from like the main process. Like in SSH agent case, we want to only the SSH daemon to access. This brings us to Linux kernel key retention service, which is the official name for Linux kernel keystore. So, and the idea is plain simple. So we take the agent model here and replace the process 2 with the kernel, which is also in a different address space, right? And the well-defined interface, it already exists. It's called system calls. So, and this is basically it. So Linux kernel key retention service can store cryptographic keys as kernel objects, and it was initially designed to share keys with in-kernel system, like full disk encryption or encrypt.fs, but then it was extended for user space application to manage their keys or secrets. And the basic idea is that because the keys are now stored outside of the process address space, they're protected by the kernel, they're real kernel objects, they have access permissions similar to files, and you can have a really fine-grained access to those keys. And the main advantage is the key lifecycle in the kernel is bound to some kind of lifecycle of the process itself, which we'll see later. Surprisingly, for a kernel feature, it has a really great documentation. So, yeah, and the basic idea between the keys, behind the keystore is the keystore categorizes the keys into like key rings and keys. So you have the top-level key ring, and then you have it may contain other key rings, and then these key rings can contain keys. Similar to like a file system structure, but specifically for keys. So key objects is basically contain. It's our kernel objects that contain actual cryptographic material. They can be read, written to, or used. There are different types of keys, which I will just touch in this presentation a little bit later. And as an analogy to a file system, they're kind of filed to the file system. But unlike a file, in the file system, you can actually link the key into several key rings, where file is usually only present in one directory, which is also nice. And key rings are like directories in the file system, so it's a collection of keys. But the idea behind key rings is that they basically determine the life cycle of a key. As I mentioned, a key can be linked to one or more key rings, but if a key is not linked to any key ring, it gets automatically destroyed by the kernel. So this is how you can control the life cycle of a key. A simple example. So in this case, we create a new keyring. I create a new keyring for my user, and then I add a super secret password, hunter2, to my keyring. And yeah, I can show like which keys I have. So here's my session keyring, which I'll touch a little bit later, user keyring, my custom keyring, and my key. And the keys are determined by unique identifier, so they call it a serial number. And basically, because it's my key, I can read back the cryptographic material. I can read the secret, and I can see the hunter2. Another more interesting example, like secret sharing between the users on the same system. So we have 2 users, Alice and Bob, and they don't share anything in between them. As you can see, all the groups are different. They're not present in the same group. However, what Alice can add a secret to her user space keyring, a user keyring. What Bob can do is actually, it can create a new keyring, and we call it from others, to accept keys from other users, for example. And what Bob will do, he can set permissions on this keyring to allow every other user to write to that keyring, to put keys inside. So once he did that, Alice can actually move her key to that keyring, and we can see Alice doesn't have the key anymore because it was moved, and Alice cannot access the key anymore. And Bob can now actually read the secret because Bob has access to the key because it was moved to his keyring. So in these examples, we saw like keyring, we created custom keyrings, but there are like special useful keyring types which are implicit, and their life cycle is bound to some other kernel entity. So the most interesting are process keyrings. So you have a session keyring, which is automatically created for a process, and it is accessible from your current process and all the child processes in your process tree. There is a process keyring specifically, which is private to your process. So every application in Linux has its own process keyring, and as soon as the application terminates, the keyring is destroyed as well. And there is even a thread keyring which is specific to a thread. So for example, if you have a web server which serves like many endpoints, many different host names, but from different threads, you can even like isolate the keys for each host in the thread keyring. There is also user keyrings. So user keyrings are basically, its life cycle is bound to a particular user ID, and it's accessible for any application which is running under a particular user ID. And user session keyring is quite similar, so I won't touch too much on that. And there are persistent keyrings. These are not bound to a particular kernel entity, but rather to a particular timeout. So they are mostly useful for cron jobs where the process starts and goes, but like you don't want the key to be destroyed if you have a periodically running cron job. But if your cron job, for whatever reason, stops after a timeout, the key would be destroyed. So let's see a keyring example. So in this case, I add my secret to my session keyring, and yeah, I have the access to the secret. Now, so you can see the IDs, the serial numbers match, like my secret is in my possession now. What we can do now is in another terminal, we can set a BPF probe on a function inside the kernel which is responsible for key destruction and just monitor it. And in the first terminal, what I will do, I'll just imagine I'm SSHing into this box, so I'm just logging out, and I can immediately see that because my session keyring was destroyed, all the keys linked to it was also destroyed. And I can see that like the kernel actually destroyed my key from the BPF probe. And if I re-log in back, I can see that I don't have the key anymore in my possession because actually, even though I have another session keyring, it was actually recreated, so it has a different serial number. So when my session ended, that session keyring was destroyed, and when I connected back, I get a new session keyring. So the whole idea behind all that, if you select the appropriate keyring type, you can ensure your keys will be securely destroyed when not needed. Even if your application crashes, even if your application is written in Java or Go, and regardless of how it ends, the kernel will ensure all your cryptographic keys inside the kernel will be securely destroyed, basically zeroed out and from memory complete. So it's all good for security and also a nice way to satisfy many compliance requirements if your code is in Java or in Go. So far, we have been using user key types, which is the simplest key type in the kernel, but there are more. So what's the difference? So user key types is like, imagine you have a process and it has some cryptographic material it wants to use, so it kind of puts that key inside the kernel, and either this process or another process can read it back if that other process has proper permission. So it's also subject to permission. We have also a thing called logon keys. So the idea behind them is you can put the key inside the kernel, but you can never read it back. And this key type is mostly to share the cryptographic material with in-kernel subsystems like LUKS, disk encryption, or encrypt.fs. So if you actually have a modern Linux distribution, you can run this command, and you will see that your keys are actually handled by the logon key type. There are also asymmetric keys. So like if you have an RSA key, you can put it inside the kernel, But instead of reading it back, you don't need to read it back. You can just ask the kernel to perform cryptographic operations based on that key, like either to decrypt or sign data. And yeah, it's like a software HSM. So in this example, we can like generate a private key. We need to convert it to PKCS8 format because this is how kernel understands asymmetric keys. And we can, not me. Yeah, and we can actually add it to some session keyring, for example, and we can sign data with it, and actually then we can use OpenSSL to verify that the generated signature is valid. So RSA keys are useful exactly for writing these to replace the agent model. So in this blog post, which I also have a link in the end, a Cloudflare blog post, we actually developed a proof of concept patch for the SSH client. So you can actually replace the SSH agent with the kernel keystore. So you don't have to run an agent on your system, but you can just store your RSA SSH key inside the kernel keyring, and the SSH client will use that to authenticate to your service. So yeah, so from user perspective, it's really great, but there is one problem, right? Which we also want to address if we want to build like enterprise secure systems, is like proper key management. And the question here is how, like, of all these examples we saw that even though we have the cryptographic material, an application needs to put it inside the kernel. It means that at some point, the key material is still accessible to applications, and there is this small window of opportunity for an attacker to steal it. So how can we provision keys in a way that the user space applications will never see the plain text cryptographic material? And for that, we have another key type called encrypted keys. So the idea behind that, you already have some wrapping key inside the kernel, and the application has an encrypted blob, which is cryptographic material encrypted with this wrapping key. So in user space, it's encrypted. When you insert it in the kernel will use the wrapping key to decrypt the cryptographic material, but if you try to read it back, it will be encrypted again. Right? Good, but the problem is how the chicken and egg problem, how do you get the wrapping key inside, right? So what you can do is you can use a trusted key, and the idea is behind that, you replace the wrapping key with a TPM. Everyone here knows what a TPM is? So most servers and modern laptops have the security chip inside your computer, and that wrap key can be wrapped to a TPM. So when an application inserts that key, the kernel will use the TPM to unwrap that key. And basically, if you try to read it back, it will be encrypted again. Using TPMs is not, TPMs are quite slow, so it's not really great to use for continuously for many keys. So usually what happens is in big systems, you have this combined schema. So you have a process, you have a TPM, and then you have some kind of provisioner and like some cloud or on-premise HSM service. So, which will provide you a wrapped root key to a particular server or machine with a TPM. It will get unwrapped inside the kernel keyring with the TPM only once. And then you actually use encrypted keys. So all the other keys are encrypted with this root key, which is now a software key. And like processes can use, like this HSM can distribute these wrap blobs to applications. And these applications can insert that key inside the kernel, and it will be decrypted by the root key. So you need to touch the TPM only once, and then you can provision other keys using this software key. Good so far? There is one problem with this approach, though. Even though the applications never see the plain text cryptographic material in their process address space, the applications are still somehow responsible for contacting the centralized KMS or HSM service. So imagine if like every application developer, apart from writing their business logic, need to integrate some library or whatever protocol, API to connect to some HSM, or who uses Vault, for example? Vault, yes, HashiCorp Vault. or any like on-premise chips. And so you need to integrate the communication with that HSM to your application. And every developer needs to do it, which is cumbersome. So yeah, you need to know how to reach this centralized KMS or HSM, like the URI. And you have there is little administrative control of the created key object. So for example, if application can misbehave, it will get its encrypted blob from the HSM, but will set improper permissions, so it's like world writable, for example, or readable for any other process on the system. Yeah, and the KMS and HSM needs to somehow authenticate the edge remote application. So there are a lot of entities to authenticate. For this, there is another way to provision keys in the Linux kernel. So far, all the software we've been using, the keyctl utility, is using the add key, a system call internally. So what it does is basically the add key gives an application a way to provide cryptographic material to the kernel, either on plain text with user keys or encrypted blob with encrypted or trusted keys. But the application is responsible for getting this blob somewhere. There is another interesting system called request key. And this is like a more, in this way, application does not need to actually provide any cryptographic material. It can request a key to the kernel. All the application says is asking the kernel, hey, give me this key. And the kernel is somehow responsible to provide this. So the way how it works is, yeah, but obviously, you know, with all the different endpoints, HSMs, Vault, and other stuff, your kernel doesn't know where to get this key from, so it needs help, right? So the way how it works is, imagine you have a process, and it needs some key, so it actually, instead of providing the cryptographic material, it does a request key system call, and all it provides is some kind of free-form string identifier, which you can set up on your system later. So, for example, if it can be like a namespace like path. For example, a process one says, I need a key from cloud or app key one, right? And it issues a request key system call to the kernel. The kernel actually creates a placeholder inside for that key, but now the kernel by itself does not know where to get this key from, so it needs help from user space. So it spawns a specifically designed process called request key, and this system is actually modular, so you can actually write plugins to it in any in any programming language. It doesn't have to be in C. You can write it in Go, Java, even Bash, which services different paths. So for example, if my application requested a key which is starting with cloud, it will go to the cloud plugin, and then the cloud plugin actually knows how to contact this remote HSM service, get that key, and get that key. Probably it will be a trusted or encrypted key. So then the cloud HSM will return the key material to the process. The process will send it back to the kernel, and then the kernel will actually instantiate that key inside the kernel space, and then it will reply back to the requesting process that your key is ready. So the advantages of this approach is that now you have a single centralized operating system API to request key for applications. So you are fully decoupled from your KMS backend, and actually your administrator can now shuffle and control where actually requests are going, right? So like there is no KMS or HSM connection strings in your applications, just a free-form string ID, and it's fully decoupled from key storage backend. So for example, if later you decide, your enterprise decides to move from a cloud HSM to on-prem HSM, you can freely do that. And it's a more secure way to instantiate the requested keys. These plugins can do additional security checks and like implement any security policies as you wish. So basically with the request key, the key management itself becomes a core service of the operating. This is all I wanted to say for today. Here are some links, and everything that I presented now and like more code is in the Cloudflare blog post I mentioned earlier. So you can go, copy-paste code, try to run it, and have have fun. Thank you very much.
Thank you, Ignat.